Hello there. In this video we're going to discuss how to derive the moment generating function as well as the characteristic function for a normal random variable. So we're going to begin by assuming that x is for simplicity we're going to assume that x is a standard normal random variable. We can assume that it's a standard normal random variable because just normal random variables are just shifts and stretches of a standard normal, so the derivation would be the same for the more general case. So if this is the case, then the probability density function for a random variable x at a particular point x is given by 1 divided by the square root of 2 pi times e to the minus 1/2 x squared. So we're going to derive the MGF for this particular random variable and also the characteristic function as well. So as usual with these types of problems, we're going to begin with the definition. So if this is a probability density function, by the definition of moment generating functions of parameter t, this is defined to be equal to the expectation of the random variable etx, where t is a real number. So if that is true, then that means if x is a standard normal random variable, then the expectation, so recall the definition for the expectation of random variable x is going to be the integral from minus infinity to infinity of e to the tx times the PDF, namely that would be fxx dx. So this is going to be equal to the integral from minus infinity to infinity of e to the tx times 1 over the square root of 2 pi times e to the minus 1/2 x squared dx. This 1 over square root of 2 pi is a constant, so I'm just going to FOIL him out. So that's just going to give us 1 over the square root of 2 pi, integral from minus infinity to infinity, etx times e minus 1/2 x squared dx. These exponential terms have the same base, so I can combine the exponents into 1. So I have 1 over the square root of 2 pi times the integral from minus infinity to infinity of e to the minus 1/2 x squared plus xt dx. So this 1/2, so this is a quadratic equation, so I can pretty much complete the square, but we have this minus 1/2 term, so I can write this xt term as 2 over 2. Also, I can add and subtract a term so I can complete the square on that quadratic. So I have negative 1/2 x squared plus 2/2 xt. And then I'm going to subtract 1/2 t squared and add 1/2 t squared to this term. So that's just adding 0, so I haven't changed anything. So now I'm going to factor out a half out of these two terms, or these three terms. So I have 1 over the square root of 2 pi times the integral from minus infinity to infinity, e to the minus 1/2 factored out of, so we're going to have x squared minus 2xt plus t squared. And then I have this plus 1/2 t squared term dx. So this of course factors extremely nicely. So this is just going to be 1 over the square root of 2 pi times the integral from minus infinity to infinity of e to the minus 1/2 x minus t squared plus 1/2 t squared dx. So this term only has x and this term only has t, so I'm going to decompose this exponential as 1 over the square root of 2 pi times the integral from minus infinity to infinity of e to the minus 1/2 x minus t squared times e to the 1/2 t squared dx. Now with respect to x, this term is a constant for the integral, so I can factor it out. And also I'm going to FOIL my constant back into the integral as well. So that's just going to give me e to the 1/2 t squared times the integral from minus infinity to infinity of 1 over the square root of 2 pi e to the minus 1/2 x minus t squared dx. So what is this expression here? So this expression is a normal random variable with a mean of t. So using u substitution, you can verify that that pretty much is a normal random variable. So that means if this is a PDF, that means this integral must precisely be equal to 1. So that means this is equal to e to the 1/2 t squared times 1, which is just e to the 1/2 t squared. So in conclusion, the moment generating function for standard normal random variable x of parameter t is equal to e to the 1/2 t squared. Now the general case for a normal random variable, so if x is a normal random variable with any mean and any standard deviation, then its PDF is given by 1 over sigma square root of 2 pi times e to the minus 1/2 x minus mu over sigma squared. So I leave to the reader to verify that the moment generating function for just any normal random variable, mxt, is going to be equal to e to the mu t times e to the 1/2 sigma squared t squared. So one can clearly see if mu is equal to 0 and sigma is equal to 1. So if this is true, then that turns it into a standard normal random variable. So if mu is 0, that term in the front disappears. And then we're just going to have e to the 1/2 t squared, which is our standard normal distribution. And this is just going to be our normal moment generating function. Now, in certain scenarios, it is useful to consider the characteristic function. So remember, the definition of a characteristic function of random variable x of t is defined to be equal to the expectation of e to the I t x. So one of the special properties about characteristic functions that relates to the moment generating functions is that phi of random variable x of minus it is equal to the moment generating function of x of t. So of course, if we replace t with minus it, then we get that phi xt is equal to the moment generating function of x evaluated at minus it. So if you have the moment generating function already, you can just replace t with minus it to get the characteristic function for that random variable. So if that is the case, since if we assume that x is a standard normal RV, so if that is true, since the moment generating function of x is equal to e to the 1/2 t squared, then via this characteristic, we have that the characteristic function of a standard normal random variable t is going to be equal to e to the 1/2 minus it squared. So when you square a negative, it becomes a positive, so nothing special happens there, but I squared is equal to -1. So if that is true, then phi x of t is going to be equal to e to the minus 1/2 t squared. And again, I leave it as a exercise to verify what the characteristic function for a general normal random variable with mean mu and standard deviation sigma would be equal to. But that's pretty much how you derive the characteristic function and the moment generating function for normal random variables. And of course, you can use this to generate a useful property for the expectation or the nth moment of a normal random variable or standard normal random variable. Hope you enjoyed.